Hello. In the last episode, we discussed many electron atoms. Today, we will go on to deal with molecules. The Hamiltonian for a molecule should include terms for the kinetic energy of the nuclei, the kinetic energy of the electrons, the potential energy of electron nuclear attraction, the potential energy of repulsion between the electrons, and the potential energy of repulsion between the nuclei. Here we use the convention that capital letters and Greek letters refer to the nuclei and small Latin letters refer to the electrons. In 1927, Max Born and Robert Oppenheimer developed an approximation for treating the dynamics of molecules. They noted that the mass of the proton is very much greater than the mass of the electron. And therefore, the masses of all nuclei are thousands of times greater than the mass of the electron. Okay? And therefore, they argued that the electrons in a molecule are moving much faster than the nuclei, and the nuclei are moving much more slowly, much more sluggishly than the electrons. In fact, the electrons are moving so much faster than the nuclei that they see the nuclei as being almost stationary. To give you an illustration of this, consider this picture. This is a scene that I used to see from the window of my office when I was at Shiv Nara University. My office used to look out onto this lake, and there were a lot of birds that used to gather around this lake. And also during summer, the buffaloes used to come down to graze and drink at the lake. Now, the buffaloes are generally large and heavy, and they generally move quite slowly. And if you have ever gone close to a buffalo, you will notice that there are generally flies buzzing around the buffaloes. And the flies are thousands of times lighter than the buffaloes. And the flies are generally moving quite fast. Buzz, 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 buzz. Okay. Now, when the flies are interacting with each other, they generally are not bothered about where the buffalo is going, and the flies generally go along with the buffaloes. Okay, so as far as the flies are concerned, where the flies are interacting with each other, the buffaloes are moving so slowly that it's almost as if the buffaloes were stationary. So in other words, the buffaloes, the flies see that the buffaloes as almost stationary. What about the buffaloes? Well, the buffaloes have these flies buzzing around them, so they are moving around in this atmosphere of flies. But when the buffaloes are fighting with each other, they generally don't bother about where the flies are and what the flies are doing. So they are moving in the field of the flies, but they are effectively interacting with each other, right? That's the situation we have here in the molecular case. So in the first step, we solve the equation of motion for the electrons. Since the electrons in a molecule are so much lighter than the nuclei, they are moving so much faster than the nuclei, and therefore they see the nuclei as being almost stationary. So Born and Oppenheimer proposed that we can solve the equation of motion for the electrons without worrying about the nuclear motion, that is, considering the nuclei as being almost clamped in their instantaneous positions. So the Hamiltonian for the electrons, so the so-called electronic Hamiltonian consists of the kinetic energy of the electrons, the potential energy of attraction between the electrons and the nuclei, and the potential energy of repulsion between the electrons. Okay. So we can write the electronic Schrodinger equation as the electronic Hamiltonian acting upon the electronic wave function psi e gives the electronic energy E times psi e. The eigenvalues of the electronic Hamiltonian are the electronic energies E, where n refers to the electronic state. Okay. Since the electronic Schrodinger equation is solved for each instantaneous arrangement of the nuclei, that is for a particular molecular geometry, the electronic energies and the electronic wave functions are functions of the nuclear coordinates. Note that the electronic energy is a function of the nuclear coordinates, and the electronic wave function is of course a function of the electronic coordinates, but it's also parametrically a function of the nuclear coordinates. In the second step, we solve the equation of motion for the nuclei in the average field of the electrons. So the electronic energies and the internuclear potential energy of repulsion together form a potential surface upon which the nuclei are presumed to move with a given kinetic energy. The electronic energies together with the nuclear repulsion therefore form a potential energy surface upon which the nuclei move, and this gives us the nuclear Schrodinger equation, that is H operating on phi nu, the nuclear wave function, gives the energy times the phi nu, with the total wave function in the Born-Oppenheimer approximation being given as the product of the electronic wave function times the nuclear wave function. The support for the Born-Oppenheimer approximation comes from the observation that molecular spectra often separate out into lines that correspond to transitions between different electronic energy levels and lines that correspond to transitions between different vibrational or rotational levels within the same electronic state. Okay. Thus, here we have the electronic spectra which come from transitions between different electronic states, the vibrational spectra which come from transitions between different vibrational levels given by these dark lines within the same electronic state, and the pure rotational levels which come from transitions between different rotational levels within the same electronic and vibrational state. Okay. And these the electronic transitions require energy in the ultraviolet or visible region. The vibrational transitions require energy in the infrared region, whereas the pure rotational transitions appear in the microwave or far infrared region. Okay. So in a given, now if we include the internuclear coordinate, then we have a potential energy curve like this, or a potential energy surface, and in this electronic state we have different vibrational levels, and within each vibrational level we have rotational levels. If we include different internuclear coordinates, then we can get a multi-dimensional potential energy surface. So, for instance, here this is torsion angle 1, this is torsion angle 2, and this is the energy. Okay. So, chemists usually visualize molecular structure within the Born-Oppenheimer approximation. So, for almost all applications, the molecules are visualized within the Born-Oppenheimer approximation. For chemical reaction, again we have the different conformations forming, say, an axis here, and we have the nuclear displacements which lead to reaction of reactants going into products along this coordinate here, the reaction coordinate. So here you have the reactants, and you cross a transition state and leading to the products.